Alright, so we're going to mode lock a ND oscillator where we're using nonlinear polarization rotation to mode lock the oscillator. So over here what we've done is we're now looking at the spectrum coming out of the oscillator and the pulse train measurement at the same time. And the way that we've accomplished that is we're just taking the output and we're splitting it between what's going to the spectrometer and what's going to a fast photodiode. So first thing first, for a fixed position of the fiber, the waveplate settings will be deterministic. That is, once you've got your laser mode locked well, you should write down the settings for the different waveplates, for your birefringent filter, just so you know, and also your pump power, so you know how to get back there if you lose mode locking at some point. So I've already done that. Now I'm going to show what it looks like to mode lock the oscillator. The basic protocol is you want to have a very high efficiency oscillator, so you want good CW efficiency, and you want your high CW power to be something around 25% higher than where you expect to see mode locking. So if you expect mode locking at 150 milliwatts, you want about 200 milliwatts of continuous wave power before you start worrying about mode locking. You want a slope efficiency in your oscillator of about 30 to 40% before you're going to expect to see it mode lock easily. So what I'm going to do is I'm going to play with these two, and I'm going to constantly play with this quarter wave plate. Every now and then I might play with the birefringent filter, which is going to change the position of the filter. So it's going to change the center wavelength of the oscillator. So that's going to look something like this. And while I'm doing that, I'm going to be looking at both the spectrum and the pulse train. And so you can see, for example, right now we're clearly mode locked. Now it looks like it's on the realm of getting close to mode lock. This is what we would call self-Q switched operation, or something like this. There's very clearly something that's happening in the oscillator, but there's a narrow bandwidth in the spectrum over here. Q switching is usually very near in terms of parameter space where mode locking will occur. So if you're seeing Q switching, it's usually a good sign that you're near mode locking. So I'm going to play some more. And usually you'll end up seeing something that kind of pokes out, and then you can get closer to it. And usually by playing with the quarter wave plate here, this first quarter wave plate, you can adjust the details of the spectrum. So let's just look at that let's look at the spectrum as I play with the quarter wave plate. So you see you're going through a different range of parameters. You can see right here, we're on the edge of mode locking stability. We're getting a continuous wave peak that's coming out. So you generally want to avoid that. I would recommend for most applications that you try and operate in the most stable regime. So you could play with these wave platings to get a much better pulse, but usually it's better to not be greedy and just get a pulse that is maximally stable. So I like this. I'm now playing with the birefringent filter position, and you see I'm getting different center frequencies. So you can do that as well once you've achieved mode locking. So let's do this a little bit more. Just show you an example of what things look like. So maybe I'm playing with here. I've played with these two wave plates, and now you see I'm consistently going back and forth with this quarter wave plate over here. So that's kind of the procedure for mode locking. And there you see I found it again. So generally with these oscillators, you want to look on a linear scale for the spectrum. You want to have the fastest spectrometer you can have. You want to be looking at the pulse train at the same time. And you want to look for these kind of Batman spectra, especially with steep sides. Once you see that, you know you're mode locked. All right.